Another very common situation we'll be dealing with in calculus is taking limits to infinity. In this video, we'll review common cases, and in further videos, we'll review more complex examples to strengthen our abilities. And so here are the more common types of functions for which you'll be taking limits to infinity of, and for the most part, they're rational functions with a numerator and denominator. And so when we're dealing with limits to infinity of rational functions, the overall concept is to compare growth rates in the numerator and the denominator. So before we continue, let's do a quick review of growth rates because this understanding will really make problems less complex in addition to saving us time. So let's go ahead and take a look at this chart here, and it's ordered from slowest growing to fastest growing functions. To begin, well, if we have a constant function, so let's say it was y equals 5 or f of x equals 7 or something like that, it's just a horizontal line. And so technically it's not growing at all. And so that's where we'll begin. Next, logarithms, then linear functions, so some constant times x, and then followed by the product of those two, which is x times log x. Then after that, we start getting the polynomials. Polynomials grow much faster than these functions. So polynomials such as, 5x squared plus 2x plus 3, something like that. And as we increase the highest degree, we increase the growth rate. So polynomials of degree 3 are faster than degree 2. Polynomials of degree 4 are faster than degree 3, 2, and 1, and etc., etc., etc. And so then the fastest growing function out of all are exponential functions, where we have a constant base that's more than 1. It has to be more than 1, and it's raised to the power of x or some function. And there we go, there we have it. So our fastest growing function is an exponential function, assuming that the base is more than 1. If it were less than 1, it would be decaying. If the base was 1, well, it would be a constant function. And so like I said, in this video, we're only going to be concerning ourselves with rational functions. And so I'm going to give you a super general guideline to follow for taking limits to infinity or negative infinity of any rational function. So step 1, and so if we're taking the limit as x approaches plus or minus infinity of a rational function where we have a numerator and a denominator, and so I'm denoting f of x being the numerator, g of x being the denominator, or we could say that we're taking the limit as x approaches plus or minus infinity of some function over another function, numerator and denominator. For the sake of this video, I'm going to make this very casual, and so I'm just going to go ahead and identify the numerator with n, the denominator with d. So step one is to always check to make sure that the numerator and denominator are as simplified as they can be. So make sure you check for simplification. Next, step two, you always want to compare the highest growing terms of the numerator and the denominator. Everything else in the numerator and denominator really doesn't matter. It really does not matter. And this is because as a function grows, the highest growing or the fastest growing term will eventually take over, and it will be the dominant force in that function. So again, step number 2 is to compare the highest growing terms. So compare the highest growing terms in both the numerator and the denominator. Step 3, we're going to go ahead and rewrite that limit as the limit as x approaches infinity, or plus or minus infinity of, we're going to go ahead and just get the highest term in the numerator, or the fastest growing term in the numerator, over the fastest growing term of the denominator. And I'll go ahead and just use f. So the fastest growing term in the numerator over the fastest growing term in the denominator. And let's go ahead and get used to this notation. I'm just using this to explain it in a very casual way. I don't believe you'll find this in the textbook. Step number 4, and this is going to be our final step. And this is probably the most important one. And so I'm going to use a different color. So 3 cases that can appear now. 3 cases. The first case, well, the numerator could be growing faster than the denominator. So let's say the numerator, or the numerator's term, grows faster than the denominator's fastest growing term. In this case, our answer will either be positive or negative infinity. And it really just depends on the case, and we'll go over some examples to show you what I mean by this. Next, conversely, if the denominator's fastest term, or fastest growing term, grows faster than the numerator's fastest growing term, in this case, the limit as x approaches positive or negative infinity, it'll automatically be 0. The reason for this is because if the denominator grows faster, let's go ahead and take, for example, the function 1 over x. As we grow faster and faster and faster, well, we see that 1 is a constant, x is linear. So we can go ahead and assume that the denominator grows faster. And because of that, as we increase the value of x, as we get closer and closer to infinity, we notice that we'll have 1 over 1, which is 1, 1 over 10, which is 0.1, 1 over a million, which is a lot of zeros, but then a 1. But it's getting very, very, very close to 0, but it won't touch 0. So the limit, it's going to be approaching, but it won't touch 0. And so this case, it will hold true every single time. Every single time. And lastly, let's go ahead and say that the numerator's fastest growing term, well, let's say the denominator also has the same rate, the same growth rate. So let's say the numerator and denominator have the same growth rate. In this case, all you have to do is divide the two terms. Because there will be some simplification you can make. If they grow at the same rate, I guarantee you there will be some simplification you can make, and the limit as x approaches positive or negative infinity will just be the quotient of the numerator and the denominator of their fastest growing terms. And there that is. So let's go ahead and practice a little bit now. All right, so example number one, again, I'm going to be using my general rules, my general guideline the entire way. So problem number 1, let's go ahead and say we want to compute the limit as x approaches positive infinity of the following rational function: 3ax cubed, sorry, that's a squared, 3x cubed plus 2x over, and let's go ahead and say we have negative x plus 2. All right. So let's go ahead and follow my general guideline. Let's go ahead and say, number 1, simplification check. Can we simplify anything? Can we combine any like terms? Nope, don't see anything we can do. So step 1, we're good. Step 2, compare the highest growing terms of the numerator and denominator. Well, if we were to observe, we can see that the 3x cubed is the fastest growing term of the numerator. Negative x would be the fastest, or the x would be the fastest growing term of the denominator, and it just so happens that there's a negative on it. It just so happens that there's a negative on it. That's fine. So we have our two highest growing, or fastest growing terms. Here's what we do next. Step 3, I'm going to go ahead and rewrite this limit. I'm going to go ahead and say that this limit is equivalent to the limit as x approaches infinity of 3x cubed over negative x. The limit as x approaches infinity of 3x cubed over negative x. And trust me, this is completely fine. It is equivalent to. I did not say that these are equal because these functions are not equal. But these limits will have the same result. They will have the same limit. Because the other terms, they are not growing anywhere near as fast as the other. And so we can ignore it because we are approaching an infinite value. And so eventually negative x is going to leave that 2 behind. And the same goes for the 3x cubed. It will leave behind. It will leave 2x in the dust. So we can go ahead and just compare the fastest growing terms. All right. Now, step 4. Well, we see that the numerator grows faster than the denominator. But before we go ahead and assume, anything else, here's where that plus or minus infinity comes into play. if you took some notes. Before I go ahead and just plug in infinity, here's what I'm going to do. I'm going to go ahead and rewrite this limit. So if you remember your properties of limits, constants can be moved outside. -1 on this x is also a constant. And so 3 divided by -1, well, that's just going to be -3. And so this is equivalent, or this is equal to the limit, or -3 times the limit as x approaches infinity of x cubed over x. All right, and I'm sure that we can see that we can make a simplification here. X cubed over x, well, that's just going to be x squared. So this is, again, the limit as x approaches infinity. Oh, whoops. I forgot that -3. Don't let me forget that. -3 times the limit as x approaches infinity of x squared. And so we can go ahead and just plug in infinity for x, because we know that we'll actually get a defined value. And so the value, well, if we plug in infinity, that's just going to be infinity. So we're going to be left with -3 times infinity, which is the same as, well, 3 times infinity, that's going to be infinity anyway. And then negative, so that's going to be negative infinity. And so there we have it. The limit as x approaches infinity of 3x cubed plus 2x all over -x plus 2, it will be negative infinity. And we can go ahead and graph to confirm that. This technique works. And so let's go ahead and dive into another example right away. Let's go ahead and start our second example. So, 2. Let's go ahead and say we're taking the limit as x approaches, this time negative infinity, of the following rational function. Let's say we're taking the limit as x approaches negative infinity of 12x squared plus 5x minus 9 all over 5x squared plus 3. 5x squared plus 3. Oh yeah, and before I continue, just as a quick reminder, if you remember from algebra, when we're taking limits to infinity, that's actually the same thing as computing the horizontal asymptote of this function. It's pretty much the same thing. But for the sake of calculus, I don't want to bring things down to a very specific situation where, oh yeah, always look out for polynomials. This general guideline I give will work for any function, any type of rational function that you may see. So, we have this limit. Let's go ahead and follow my steps. Step 1, can we simplify anything? Nope, nothing can be combined, so we're good. Next, we are going to compare the growth rates of the fastest terms. So let's go ahead and circle those. In the numerator, well, it looks like 12x squared. That will be my fastest growing term. In the denominator, pretty clear here, 5x squared is my fastest growing term of the denominator. So there we go. I've identified them both. All right, next step. Next step, we are going to state that this limit is equivalent to the limit. Sorry about that. It's equivalent to the limit as x approaches negative infinity of, just comparing the two, so the quotient of the two fastest growing terms. So 12x squared over 5x squared. All right. So step 4, well, here it is. I mean, I believe that we can see very clearly that because they are the same term, x squared and x squared, they grow at the same rate, and we can definitely simplify this. And so this limit is equal to the limit as x approaches negative infinity of 12 over 5. And so, well, there's no x. There's no x at all. And because there's no variable to take a limit of, well, the limit as x approaches anything of 12 over 5 is always going to be 12 over 5, no matter what. No matter what. And so there we go. Just like that. And again, we can go ahead and confirm this with the graph. Look at this graph of the original function. Let's go ahead and see what happens as we get closer and closer to negative infinity, and boom. It looks like we're approaching about 2.4, which is 12 over 5. And so guys, I'm not joking. Memorizing this growth rate chart will be key moving forward as you continue to tackle limits. And then as you go deeper into calculus, I promise you this will come up again. And so memorizing these growth rates will go a long way later on because you'll understand what's going on in deeper calculus. So let's go ahead and take a look at one last example for the sake of this video. And let's go ahead and say we're taking a look at the limit as x approaches positive infinity of, let's say, 4x to the 10th power minus 29x to the 12th power plus 50x. And this is going to be all over, let's say, 3x to the 12th power plus, let's say, e to the x. E to the x. All right, cool. So we have our limit, we have our function. Let's go ahead and see what we can do. Step 1, simplification check. Can we make any simplifications? I don't see any in the numerator. I don't see any in the denominator. When I say simplify, I mean combine like terms. Yes, we can pull out an x from the numerator, but that's not what I'm looking for. It's all good. All right, step number 2. Let's go ahead and identify and compare the fastest growing terms of the numerator and the denominator. So in the numerator, let's see, degree of 10, 12, and 1. So this negative 29 x to the 12th power is my fastest growing term in the numerator. In the denominator, we have 3x to the 12th power, which is a very nice term. And then we have e to the x. Well, let's go ahead and consult that chart one more time. Remember, exponential functions grow the fastest when the base is more than 1. E is the natural number. It's approximately 2.71, and therefore it's more than 1. So e to the x takes the cake. This could have been 3x to the 99 power. It could have been to the 125 power. Either way, e to the x will still grow faster. So we have to wrap our heads around that idea. We have to moving forward. So step 3, we are going to state that this limit is equivalent to the limit as x approaches infinity of negative 29 x squared, or x to the 12th, sorry, all over e to the x. So this limit up top will be equivalent to this limit. Up next, what I'm going to do is I'm going to go ahead and save myself a little bit of trouble. I'm going to remove any constants, any negatives, by just factoring it out outside of the limit. Because remember, the limit of a constant times a function is the same as the constant times the limit of the function. That is one of our properties of limits. So this is equal to negative 29 times the limit as x approaches infinity of x squared, or x to the 12th, over e to the x. All right, so now let's get to business. We have this limit, we have two terms. We know that e to the x will grow faster than x to the 12th power. And because of that, going back to our rules, our general guideline, if the denominator grows faster than the numerator, the limit as x approaches infinity or negative infinity will automatically be 0. And so this is equal to negative 29 times 0, which is still 0. And again, the reason that this automatically approaches 0 is because eventually, because the denominator grows faster, the denominator will outgrow it. Eventually, this will start to become a very, very, very lopsided fraction where the numerator is relatively small and the denominator is relatively huge. And because of that, that means we have a very small number divided by a very big number, which will eventually approach 0. And again, we can use the graph to confirm our thoughts and our little conclusion here. And boom, as we get closer to infinity, we see that this function is going to be approaching 0. And there we go. So I hope we see that this general guideline works. I really, truly hope we see that that guideline works. And so for a brief recap, everyone, for a very, very brief recap, what we did in this video was we tackled limits to infinity of rational functions. Now, there are other types of functions that we will be taking the limits to infinity of. There are some basic examples as well, but I really want to dive into, in the next video, limits to infinity of trig functions and other unique functions that you will definitely see in this course. So again, our nice little 4-step process goes as follows. Step number 1, make sure you check for any simplification you can make in terms of combining like terms in the numerator and the denominator. Next, we want to identify and compare the fastest growing terms of each the numerator and the denominator, because the limit to infinity or negative infinity of whatever you have will be equivalent to the limit as we approach infinity of the fastest growing term in the numerator divided by the fastest growing term in the denominator. Plain and simple. And that was step 3, defining that equivalence. Then step number 4, we just compare them. We truly just compare them. We will go ahead, if the numerator grows faster than the denominator, our limit will be equal to either plus or minus infinity, or positive or negative infinity. It really depends on the situation, depending on the constants that you pull out. If the denominator grows faster than the numerator, this limit will automatically be 0. Automatically. And that's because if we divide any number by a very, very, very large number, it will be approaching 0. And then lastly, if the numerator and denominator have the same growth rate, or if the fastest terms have the same growth rate, well, it's our lucky day, because all you got to do is just divide those two, and that's it. You're good. I guarantee you something will simplify. And so that's it. Thanks for tuning in. There will be a next video on trig and other unique functions with limits to infinity. And just keep practicing, watch that next video, and we'll see you next time.